Welcome back, everybody. So in the last lecture, we talked about the water cycle in general and specifically how much fresh water falls on land, about 100 cubic kilometers per year, and how much of that returns to the atmosphere as evapotranspiration versus how much runs off, so the 60-40 rule. So today we'll look at the freshwater distribution. So the freshwater that is actually on land, how is it distributed? And this is sort of the big numbers. I know that's a lot of numbers to remember and they're slightly different. But again, the oceans are obviously, the salt water is the majority. Remember the blue marble. So the freshwater is only a fraction of that, so 3%. Now, of that freshwater, most of it is ice, so solid, right? And then the groundwater is a large part. So that's where this brown bar here is sort of the focus of this class, right? The 30% of freshwater, roughly 30% of freshwater is actually groundwater. And you can see that the surface water, so the running water and other freshwaters, is really a tiny fraction of the total freshwater. So again, the freshwater, mostly ice, mostly solid, lots in the ground, and then a little bit moving around as rivers. Now, one way I like to remember those numbers, because again, that's a lot of numbers to remember at once, is to think about, physically what does that mean, right? So if all the water on Earth is the size of the Empire State Building, right? So that's a lot of stories, 100 stories, 1,500 feet, right? That's about 1.4 billion cubic kilometers. Now the freshwater is only about 1 to 2 stories of that, right? So only 20 feet, so a small fraction, a few percent. Then out of that, right, the groundwater is about the size of a person. So again, it's about a third, 30%. So a third of a 2-story, right? So 1 story is about two people. So roughly the groundwater represent, 1 person next to the Empire State for the whole water and next to a couple stories or a story, big story or 2 small stories. That's the amount of groundwater. Now the surface water would be the size of the wallet, right, in the pocket of that person. So again, that gives a sense of, if you remember the whole building for the water store, the 1 to 2 stories for the groundwater, a person for, excuse me, I misstate. So 1, 2, 3. So if all the water is represented by the Empire State, right, the fresh water itself is only a story or 2. The groundwater is the size of a person, living in those buildings. And then finally, the surface water, so the running water, the lakes, etc., is only about 1%, so just the size of the wallet. Okay. Now, a quick example just to illustrate, how much water there is in the world, right? Let's say we didn't know how much water there is on Earth. Well, we could do a simple calculation, right? So this is obviously a rough map of the Earth where I just Google map, the size of the continents, and you could obviously just Google it and find their sizes, but roughly this is what they are. If we assume the porosity is 20%, so porosity, I haven't talked about porosity yet, but that will be a big topic in this class, and I'll do some specific lectures in the second module of this class, so we'll talk about it. But let's assume that porosity is 20%, so the voids, right, in the material is about 20%, so that's the room that the water has to occupy pretty much. And the effective depth is 100 meters. When I say effective depth, I mean that's the depth at which we can get the water. So this is an important concept for this class, which is groundwater is often defined as an effective resource, right? So this is really the water that we can extract from the ground. It doesn't mean that this is all the water there is in the ground. So oftentimes it's limited by the depth of the wells that we can use, etc. So a lot of times aquifers are defined really practically or effectively for engineers. Anyways, in this case, just assume there's water down to 100 meters. In reality, it's much more, and we'll talk about it in a minute. Now, if you do these calculations, right, how much water there is? Well, you can just, the volume of the water is just the porosity, so 20% times the volume, right? So the depth, the effective depth, and the surface area of all the continents, that will give you a number, right? Now again, if you assume the effective depth, if you assume you can reach water down to 200 meters, right, you have twice as much water. So again, this is very, this is just a rough calculation that doesn't have a lot of ground, but you'll see in a minute that this is actually essentially how we calculate, the water resources up to recently. Now, if you look at the distribution of groundwater, so this is a table from the Corzoon paper 78, and the point here is that this is exactly the methods they use pretty much to calculate, how much groundwater there is. So this is a very important paper because a lot of people cite those numbers, although as you've seen before, those numbers are really based on rough assumption about porosity and the size of continents and how deep we can go. So again, in Europe, right, you get the total area, 10.5 million square kilometers, and if you have 15% porosity down to 100 meters, and then 12% and then 5%, and this is because there's compaction down, so the porosity is lower and lower and lower as you go as you go low, then you can calculate basically the volume of the zone exactly like I just did, and the total volume of groundwater, and you find a total down here of 23.4. So if you do the calculation, in the previous slide, you'll see that this is pretty similar to what you would find using that coarse approach. Okay, so here I'll use a couple of more recent papers to illustrate, how rough those estimates are. So this first one here, uncertainty in global groundwater storage, right? So this is exactly what I was talking about. There's a lot of uncertainty. We don't really know how much there is really. And again, this highlighted, quote from this paper, we have shown that transparent knowledge on groundwater stocks is lacking in the majority of the world's large aquifers. And this work clearly demonstrates that it is no longer adequate to continue citing decades-old, heuristically derived, highly uncertain estimates of total groundwater storage. And that's basically the estimates I just showed you before, right? These are really based on rough estimate. We say, oh, well, if we can pump down this much and the porosity is everywhere this much, then this is the volume. But really, that is not a very good estimate. An example of that is the California aquifers. So now that with modern technology, we can pump down to much deeper depth, right? So instead of 100, 200, 300 meters that we might be able to pump with sort of classic technology wells, now we're able to pump to thousands of meters almost, right? So really deep wells. And that's used in the oil industry, but of course also in the water industry. And this is an example where they calculate, the new reserves that you can count on if you could drill, this deep basically. And there's a lot of deep groundwater there. Finally, a couple of other examples of new modern ways to measure how much groundwater there is. And this is a neat paper that uses basically the Earth deformation. So it's like satellite triangulation pretty much of the Earth level. So if there's compaction, so if water dries, if the aquifer dries, the whole formation is going to shrink, right, to crumble on itself because there's no more water to sort of prop it up. So you can calculate millimetric changes year over year, and this way by correlation essentially of the depth of water in the wells versus satellite image, you can see here on the right that the correlation is excellent. So using those new sort of satellite imaging techniques, we can actually sort of calculate where that water is, because again, water table is underground, so it's pretty hard to find unless you drill. Another interesting paper, recent paper, is a 2018 Nature paper by Rodell et al. That shows sort of the changes in water reserves, again from satellite techniques. Here's what we call the GRACE satellite, so Gravity, Recovery, and Climate Experiment. And these are basically, it's similar to what I said before, but instead of measuring directly, the Earth's surface, change, you're really measuring a gravity field, if you will. So there's two satellites that triangulate again, and the water being the density it is, right? We can basically estimate a volume of water by the change in gravimetric pool. So this is how the gray satellites work. And this is sort of the results of that paper, and you can see a much more granularity here Again, this is over a fairly short period, so this is not the be-all and all of what is going on in the world, but this is a neat indication, neat map of where is the groundwater reserves receding or the water reserves receding. So these are the red spots, and you can see ice sheet melting, for example, up north and down south. You can see here in the Middle East that would be pumping of fossil groundwater, basically. So if you pump too much, right, then your water table is going to go down. Here, water depletion, some droughts, and you can see that patchwork, right? So it's not going down everywhere. There's also places where the climate adds more rain and more groundwater over time. And again, this is over a fairly short time, so 2002 to 2016. So this is a 14-year period, time frame. So it's pretty long as far as data and science goes, but as far as water cycle and earth cycles, remember the El Nino events that are on a decadal time scale. So we're looking at about 1 or 2 El Nino events here. So it's not complete, but this is a really neat indication of new techniques basically to estimate properly how much groundwater there is. Okay, thank you. I will see you in the next video.